Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about calculating combined stress step by step. Very simple. In the previous video, I calculate combined stress due to axial load and bending moment and show you how to combine these two normal stresses. In here, I wanted to talk about a shaft which is subjected to a transverse load, shear force load, and also to a torsion, 9,000 pound inch. And the force is 1,500 pound. We wanted to calculate the stresses due to each of these loading and then show how to combine them. In design, we need to combine stresses because to predict the failure and what's going on inside the material, we have to reach at least to only one stresses. This is why we combine stresses. Then we have a normal stress and shear stress inside the material. Again, we combine them to reach the worst case scenario by Mohr circle. And then we combine them to reach only to one stress, which we called it later von Mises. Okay, let's start here. Is a tube. Outside diameter 2 inches, inside 1 inches. Force that applies 1,500. Torque is 9,000 pound inch. Then you know the shear stress due to torque, tau, is T rho over J. Because we are going to consider only the worst case scenario in design, we have to calculate the tau max. Tau max is when the T torque is max. It's the same. This torque is a free vector. It's the same in all through the length of the tube, then 9,000. But rho is the maximum distance from the neutral axis of this, actually from the beam, which is 2 inches. And J, we have a two circle here. And you know J, this is 1 inches, this is 2 inches, and polar moment of inertia of the area, polar moment, the inertia, the area is equal to pi over 2 RO to power 4 minus RI to power 4. If you write it in terms of diameter, dO to power 4 minus dI to power 4 divided by 32. Then J calculated and is equal to 23.56 inch to power 4. Okay, if you substitute this here, this is pound inch, this is inch, and this is inch to power 4. You have stress pound per square inch, which is equal to, if I can find, it's 764 psi. Okay, that's the value of stress. In each cross section, if you want to show these stresses, we can show the distribution. Under the skin is equal to 764 when radius or distance is maximum 2 inches. And here, when it is 1 inches, it reaches 2, you can just half it. And then here is 0. If you attach them together, you have this distribution for shear stress due to torsion inside the beam. And here the same, if I show that this point, exactly the same story. And at this point also the same. But here that there is no material, there is no shear stress as well. There is no reason to use the mid of the shaft in the center when it doesn't carry considerable amount of shear stress. We need the mid of the metal here outside, close to the outside of perimeter of the shaft, the cross sections. This is why they made shaft hollow. And this metal that is here, there is no advantage to use that. Make the design heavier, expensive, and doesn't carry considerable torque here close to the center. Torque considerably carried by the mid, which is outside, far from the center of the shaft. This is why they made shaft hollow. Okay, this transfer shear force also produces shear stress that you know. If I consider the shaft here, this force, part of it always through the whole length of the shaft, this shear force is equal to 1500. I wanted to show that inside, you know that inside the material, the transverse shear force also produces horizontal shear stress. And that horizontal shear stress in an element that I show it like that, it is also produce shear stress perpendicular to that because of the static balance that we must have. The horizontal shear stress produced inside the material horizontally, but there must be vertical also stress that fight with it. Assume that I draw an element here from outside this horizontal shear stress. Okay, at each level, they are equal. But they produce a torque here. And this torque must be for this material because we say, if a beam or member is under static equilibrium, any portion or particle of that also must be in a static equilibrium. Then this element must be in a static equilibrium. For that, there must be another inside the material shear stress that is equivalent to this and produce an opposite actually torque on that element that produce the balance for that particle. This is why we calculate horizontal shear inside the material. And when we wanted to show, we show the vertical one, this one. Okay? Yeah. I calculate this amount of horizontal shear stress inside the material. You know tau due to transverse shear load is equal to V shear force at each section of the material, which is equal to 1500 times Q divided by I divided by P. Here is the side of the cross section that you cut exactly at when the tau is maximum. We are again here also, we are looking for worst case scenario that tau is max. When tau is max, V must be max. That is the same for the whole length of the shaft. Q must be max, and I is the same, and B also depends on the location of the tau max. There, where it is max. When you draw horizontal shear stress inside these cross sections in the shaft, it is maximum at neutral axis of the cross sections. Here, the maximum happens here. It means that I have to cut the cross section at these two. This is my B. 2 minus 1. From here to here, 1. From here to here is 2. Thus the thickness is 1, and B is equal to 2 times 1 inches, 2 inch. This is B. I, you know that, is equal to pi DO4 minus DI4 divided by what? 64. If you write it in terms of diameter. If you write it in terms of radius, actually, it is 2r to power 4. Is 2 to power 4 is 16. And then this should be 4. Doesn't matter. Then calculations of I is equal to 11.78 h to power 4. We calculate tau with the 1500 pound Q. How calculate Q? Then I write I here, do not forget that I is 11.78. B is 2 inches. This is inch to power 4. This is pound, and Q, which is inch to power inch cube. Let's calculate Q here. When we cut from here, Q is this area times its centroid with respect distance of the centroid with respect to neutral axis. The easiest way, maybe you cannot find it easy, the centroid at the end. Take your time, especially when you are in exam. Then the easiest way that we give the table, consider a circle, of a circle. Its distance is 4r over 3 pi. And area is equal to 2 inches. Pi 2 to power 2 divided by 2. Because half a circle. Times Q, which I call it Q1 and A1, is this amount, pi 4 divided by 2 times 4 radius 3 pi. And if you cancel out pi together, and r is equal to 2 inches, then you have 16 to 32 divided by 6 inch cube minus the inner circle, which is the same story again, and A2 here is equal to pi radius 1 to power 2 half of it divided by 2, and Q2 equals this area, which is pi over 2 times the distance from the neutral axis, which is 4 radius divided by 3 pi, 4 times 1, 3 pi. Cancel out pi by pi, and then we have 4 divided by 6 cube inch. Then, if you subtract these two together and each other, you have 32 over 6 minus 4 over 6 you reach to the value 467. Q is equal to Q1 minus Q2, 4.67 cube inch. We need this value here. First moment of the cross section. That's a name. Then this stress is equal to 297 psi. Approximate. Then we calculate two shear stresses. One due to torsion, another one due to transverse shear force law. Apply here. Then these two types of shear stress, they are actual, the name is shear stress. Inside the material, they combine together. We must consider which point we are considering and which point is the governing point of the design. Which point is the worst case scenario actually. Let's do it at 4 points at the moment. I consider the cross sections. I do not need these calculations anymore. Get rid of this distribution. Then we have two numbers here. Tau due to torque equals to 764 psi, and tau due to horizontal shear stress is equal to 297 psi. Okay, I show you calculations. I do not need them anymore. I show you combination of that. Okay, I draw the cross sections of the shaft again. And then at 4 point A, B, and C, 4 points, D, I show the situation of stress. Torsion acts in this way. We have a torsion TC over J, 764. What about the horizontal shear? Horizontal shear stress, when the Q, at this point, the Q is 0. When you cut it here, the cross sections, Q is almost 0. Then there is no shear, horizontal shear stress at this point, 0. At A, this is 764 due to the torque and 297 due to horizontal shear stress. They act opposite together. At C, we have the torque, 764 stress due to torque, and also 297 due to horizontal shear stress. Here they add together. And here again, we have 764 due to the torque, and nothing here because Q here is 0. If you calculate here the total, Q will be 0. Then this is the distribution of shear stress inside the material due to torque and horizontal shear stress. Which point is critical? Point C, because they added together. And we must also consider the bending as well, bending stress also as well, because this is not the end of the story. And we take these stresses at point C and combine it in the more circle with axial stress due to bending and axial load. And then we reach, later you will see we reach to new stresses, which is called principal stresses. And these principal stresses is considered for design of the members. We convert them into only one stress. We must have only one number in order to compare it with the yield strengths of the material to predict that the failure happened or not. Combine these principal stresses to one stress only, which is called von Missen's. Okay? To predict the failure. Then, this is called combined stress due to torque and transverse shear force. Thank you for watching. See you in the next video.